Hey guys, Larry C here. I have a buddy who's a mushroom, and I like hanging out with him because he's a pretty fun guy. Shout out to you all, Stat Cats. Enjoy the video.
Come on now, dog. Come on, man.
What's going on, Stat Cat? Shout out to you all. Welcome back to another installment of Build a Statistics course with me. And hey, this is a pretty exciting day because we are starting Chapter 4, which is on not my favorite topic in math, but I still respect it a whole lot, probability. So I hope you're excited because I can feel that you probably are. I know it's kind of a stretch. Anyway, so the first section is on basic concepts of probability, and I'll take you through some of the stuff that I had in store for this one. And man, I hope I hope you see that I got a little bit creative with this one. And to be honest with you, this was inspired by my daughter, who recently turned 16. This is not a dad joke, by the way, but she's really into blind boxes, and I'll get to more of that in just a moment. But yeah, so basic concepts of probability. So you probably heard me mention in one of my earlier videos that I'm currently reading a book on super forecasting, and I can show you what that book looks like, at least the audiobook format. Super Forecasting, The Art and Science of Prediction. And what's really interesting about this is that it's a really slow read for me because, number one, I'm kind of a slow reader to begin with. Number two, there's not a killer amount of math, so because of that, I'm not totally enticed with the content. And three, when I read textbooks like this, some of the problem with it is that I have a hard time with some of the concepts that aren't like immediately applicable, and so it's been taking me a while to get through it. But shockingly, when I started doing my research on the Chapter 4 from Elementary Statistics, 14th edition by Mario Triola. Remember, they don't pay me to say that, but this is fair use. Shout out to the Coach Gang and the Money Mindset for keeping me informed as to needing to say that. And yeah, shout out to you. Okay, so anyway, as I'm doing the research in Chapter 4, I'm starting to see a connection between what I'm reading in this textbook, this book here, and the textbook itself for statistics. And I wanted to bridge some of what I've learned in the notes here, and I think I did it to a certain degree of success. So I read something in the book that said Harry Truman once joked that he wanted to hear from a one-armed economist because he was sick of hearing on the one hand, on the other. And basically what's going on here is that in the book Super Forecasting, they're talking a little bit about probability and how for a long time people were just kind of going on gut feelings about certain events involving war and political decisions and things like that, until they weren't. They thought that maybe they could get a little more mathematical about it, and so they started having better informed decisions when probability was involved. And now probability is basically the likelihood of an event occurring. And as I have defined here, it's a measure or estimate of the degree of confidence one may have in the occurrence of an event measured on a scale from 0, meaning impossible, to 1, meaning absolute certainty. And there are some misconceptions about probability. The book talks about how there are basically like 3 modes of probability that people default to. 1 is not going to happen, 2 is might happen, and 3 is will happen. But, there's a lot, we can get a lot more granular about that. And so, in the book, when it's talking about a decision that Truman had to make, the different people in this cabinet were expressing their confidence in an event happening in terms of probability, but not all their probabilities were the same. There are some people saying that the event has a likelihood of 60% occurring. Another said 80%, I believe. Someone else said something lower, like 40%. And so it might not be helpful when you get all those different probabilities, but it's better than saying, yeah, it's going to happen or it's not going to happen, because you really don't know, and so you're given the likelihood. So apparently, Harry Truman was, kind of sick of the, well, it could be this, it could be that. He wanted something more decisive. All right, and so there's my long-winded explanation as the connection to this quote. So I thought it would kind of be a good lead-in for this section. So now some stuff from the textbook itself. One of the most important applications of probability in our study of statistics deals with something known as hypothesis testing, and we'll definitely be doing some videos on those, but it's going to be some time before those are produced because got a lot of groundwork to lay before that. So the author tries to emphasize this point that probability is going to help us rule in or rule out chance as an explanation to an event occurring. And so I built the first page mainly based on that concept. And I decided to call this subsection Analyzing a Claim. And this is taken from our textbook. It says the Genetics and IVS Institute's microsort exort gender selection technique, say that 5 times fast, was a sperm sorting technique developed to help couples select the sex of their future child. In particular, specifically those that wish to give birth to baby girls. They made the following claim and hypothesis. Now, this is definitely something that happened historically, and I got some of this information not only from our textbook, but I did some online research because the textbook just mentions microsort and the exort stuff, and I really wasn't sure where it came from, so I had to kind of dig that up, and last I learned it was the Genetics and IVS Institute's program. And so it's kind of similar to IVF, and basically their claim is that they can increase the likelihood of a daughter being born. And so from the textbook, specifically, they say we have developed a gender selection method that greatly increases the likelihood of a baby being a girl. Now, I want to emphasize that this was a particular technique that was being used, but due to some ethical reasons and things of that nature, they no longer offer this service. I'm not even sure if they're still running. The company is. But the hypothesis that they are using when testing this claim is that the method of gender selection has no effect, so that for couples using this method, about 50% of the births will result in girls. And so I think it's all common knowledge that, when somebody is pregnant, there's an equal chance of the birth being a boy and an equal chance of the birth being a girl. And so if this technique is, effective, then we should see something different than 50% of the births resulting in girls. Hopefully we're seeing more girls being born. And so there's this nice diagram in the textbook that I screenshotted and wanted to include in here, the different gender selection methods tested with 20 births. And so test A is referring to the exort technique. And it says, okay, well, let's assume that, 20 girls were born in the 20 births, all right? And I'm not sure if that's exactly true with the exort program, but the idea still stands. The probability of getting 20 girls by chance is 954 in 1 billion, which is a really, really small number that's very close to zero. And so chance is rejected as a reasonable explanation. So, this is a very, very rare occurrence to get 20 girls and 20 births. And so, if it were just left up to chance, we wouldn't see it skewed this much. So if this is a result, then, we can assume that the gender selection method appears to be effective. Whereas if we do a trial like this, where, there's 20 births and 12 girls are born and 8 boys are born, well, the chances are a lot greater for something like this happening by chance. So chance is not rejected as a reasonable explanation. So this is something that could occur naturally without any sort of force. So we can't conclude that the gender selection method is effective because, well, this could have just happened out of the blue. So it says here, statisticians reject explanations based on very low probabilities. And that's something we're going to close the loop on later on in this section. So what I decided to do was to allow myself some time in class to explain the idea here. It's a good intro to some of the probability stuff we're going to encounter in this section. But also I wanted us to jot down what some of our observations were and how this should be correctly interpreted. And I thought it would probably be a good opportunity to include the 5% threshold. So a common probability threshold is 5% or 0.05. So if a probability of an event happening is less than that, then something is being influential. Okay, so it's not likely to happen just by random chance. All right. So then I get into the basic concepts of probability, where I give some definitions. So this is supposed to be an event, I believe. Yes, an event is any collection of results or outcomes of a procedure. Very generic, vague, and I'll be honest with you, I have to kind of envision something to tie in with that in order for it to sink in, which I have something for that in just a second. This next definition is for a simple event. So this is an outcome or an event that cannot be further broken down into simpler components. And then this last one is the sample space, which consists of all the possibilities, so all possible simple events. So this is the sample space for a procedure consists of all possible outcomes that cannot be broken down any further. So sorry if I'm kind of rambling and not making sense. I'm having a really bad allergy attack today, so kind of pushing through that. All right, but we will persevere. So I wanted to tie in some notations with this, and the notations are taken from our textbook. So a probability, we'll fill that in together. That's capital P. And then I'm going to write out capital A, B, and C, letting them know that a lot of times events are simply denoted by capital letters. And then we blend these two for probability notation. So the probability of an event A occurring would be, P of A. So something very simple like that. I also want to emphasize that probabilities are always going to be between 0 and 1 inclusive, and we'll write down the compound inequality version of that here. And also, this is probably obvious, but sometimes I like to state the obvious because, sometimes the obvious is not obvious. Probabilities are either expressed as fractions or decimals. And then I'll probably mention a little bit about rounding conventions for these, which there's a good bit about rounding conventions in the section itself, but I think it's something that you can just use as a teachable moment and explain on the spot. So with that, we kind of phase into the 3 common approaches to finding probabilities, and this is where I got a little creative, but I won't reveal how just yet. It says, in addition to the above information, there are 3 common approaches, which are the relative frequency, classical, and subjective approaches for finding probabilities. Now, the text itself does give definitions as well as some context with pictures. Let me show you where those are at. Oops, 147, that should say. Yeah, okay. All right, 147. Right here. So 3 approaches to finding a probability. It's on page 147. The relative frequency approach. We kind of give a little definition here, an example. The classical approach. Again, definition as well as picture for an example. And then a subjective probability, same idea here. So a definition as well as a picture as an example. Which these are fine, but I wanted to give something that's a little more tangible for students. This all is stuff that well, I hope they don't experience this, but this is all stuff that we're aware of, okay? And it's not very exciting to me, in my opinion. So what I did is I went to ChatGPT because I really like the way ChatGPT creates pictures, and I asked it if you had to create a picture for three approaches to finding probability, which are relative frequency, classical, and subjective, and they'd be understandable to freshman college students, what would you come up with? And so it kind of gave this as the first diagram, which I really like the subjective one, but these are so commonplace that I just wanted to do something different. Um, so I asked it to create a couple others. One that is easy for students to see in black and white print, um, but it just really wasn't hitting the mark. So one of the ones that it gave me was this, which I decided to settle on because I think all three of these are probably a little more interesting to students than what the textbook has. So I decided to just copy and paste this into my notes. So we'll spend some time in class discussing each of the three methods for finding probabilities. We'll discuss the examples. And something that I really, really liked that ChatGPT did was this down here. Which approach should you use? And so it says have data from the past, use relative frequency, all outcomes equally likely, use classical, not enough data, use subjective. So that's kind of like gut feeling stuff or, your own life experience. Um, so we're going to go through this, and I figured we'll follow it up with some examples, okay? At the end of page 2, that's a lot of information, but not a whole lot of action. So we definitely want some action here. So I picked out 3 examples from our textbook. So suppose a couple has 3 children and assume that boys and girls have an equal likelihood of being born. Find the probability that when a couple has 3 children, there is exactly 1 girl. Express your answer as a fraction in simplified form. And something that I'm thinking about doing is including a QR code with like a YouTube short on like a gender reveal fail, because I find those very funny, and I think the students would too, and so it's a nice comedic break. But this isn't exactly how the example from the textbook is worded. I actually left it a little more vague. There's a little more hand-holding to this problem in the textbook. And that's because I want to get them accustomed to building sample spaces on their own, and then, determining which probability approach makes the most sense, and so on and so forth. So I left us some space for that. This one is taken exactly from the textbook. So in a recent year in the United States, 83,600 passenger cars rolled over and they crashed, unfortunately. 5,127,400 passenger cars did not roll over when they crashed. And so find the probability that a randomly selected passenger car crash results in a rollover. And I really like this follow-up question to it. Is it unlikely for a car to roll over in a crash? So we're going to kind of use that 5% threshold for that. And I like this example too because a lot of people might just make the mistake of taking this number and dividing it by that. But what you have to do for the total sample size is you actually have to add these two first and then use this as your numerator. And then I took this one as well because I have a lot of students that are probably going to be in some sort of medical field or medical adjacent field. And also, this was probably the only part of biology that I actually understood. And I think it's because I had math with it. So this is basically on different colors of the eyes and dominant versus recessive genes. I'll read it out loud. Each of two parents has the genotype brown or blue, which consists of the pair of alleles that determine eye color. And each parent contributes one of those alleles to a child. Assume that if the child has at least one brown allele, the color will be dominant and the eyes will be brown. And so it's kind of a little bit of hand-holding here, but I'm fine with it this time. It says list the different possible outcomes and assume that the outcomes are equally likely. So we're definitely going to make a Punnett square here. So I'm really excited to unveil that to them. And then we'll use the Punnett square to answer parts B and C. What is the probability that a child of these parents will have the blue-blue genotype? And then what is the probability that the child will have brown eyes? And then I get to use my older sister as a real life example of this, because my mom has brown eyes and my dad has blue eyes, and my sister ended up with blue eyes. So there we go. All right. So then it's important to talk about complementary events, in which case I'm bringing in a Venn diagram for that, which I always joke with my son. I look at these diagrams every now and then, and it'll give me the buzzer. The definition of it: the complement of an event A, denoted by A bar or A superscript capital C, consists of all outcomes in which an event A does not occur. And this is a really important component to finding some probabilities. So much so that I'm going to add in a rule here where the probability of an event A plus the probability of its complement is always equal to 1. And that's a very helpful rule that we're going to be using later on in the course. Now, earlier in the section within the actual book itself, they give kind of like a likelihood scale here. And I really, really wanted to put this on page 2. But as you can see, there's not really a good spot to put it. So I was like, well, maybe I'll make a note to myself to print it off on a separate handout and maybe pass it out as a little slip of paper. But as luck would have it, when I was looking for an example involving the complement, I found a great spot to place this. This is a great opportunity to bring it here. So here's the example. In a Pew Research Center survey of internet users, 3,732 respondents, that should be gone, say that they use social networking sites, and 1,380 respondents say that they do not use social networking sites. What is the probability that a randomly selected person uses a social networking site? So I'm actually going to invoke this rule to help us out with that. It says, does the result suggest that it is likely with a probability of 0.5 or greater? So I was like, jackpot. Okay, now I can bring this scale in. So we'll interpret that as 50% or 50-50 chance. So does the result suggest that it is likely for someone to use a social networking site or use social networking sites? So based on our probability and this scale, we'll determine whether that's yes or no. So the last thing before my hopefully innovative idea is the rare event rule for inferential statistics. And this kind of closes the loop with page 1, where it states here that statisticians reject explanations based on very low probabilities. And so very low probabilities allow us to infer whether or not something is having an impact, okay? So something such as the XOR program, all right? If they're finding that the number of girls born to a certain sample size has a probability that is very, very low, then the random chance is can probably be ruled out, all right? So it's basically saying whether it's effective or not. So going back down here, this is taken directly from the textbook. If, under a given assumption, the probability of a particular observed event is very small, maybe I'll underline that for emphasis, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. And this is quite wordy, so as I'm reading it, I'm thinking maybe we can do this live. Let's copy and paste it into Claude and see if maybe Larry C returns. Yes, sir. Okay, I'll say, can you abbreviate this statement without losing its integrity? We'll see what it comes up with. if an observed event would be highly improbable under a given assumption, its occurrence casts a doubt on that assumption. I don't like that. Okay, if an event's occurrence deviates significantly from what an assumption predicts, the assumption is probably wrong. Okay, this, I don't know, that's better. Say, can you give it to me so that a 5-year-old can understand it? I've never done this before, but why not? If you guess something and then something weird happens that you didn't expect, your guess is probably wrong. Oh my gosh. that's pretty dope. I like that. Um, I don't know. I'll think about that. I'll think about that. Okay, I'll say something a level more sophisticated, please. If you make a guess about something and then what actually happens is very different from what your guess predicted, that's a sign your guess was probably wrong. Okay. You know what? I'll kind of sit on that. Let's keep this gravy train rolling. All right. So in this part of the section for the textbook, it also defines significantly high and significantly low based on probabilities, and I believe the 5% rule. Yep, 5% rule. Which I should mention that 5% is just something that was conventionally assigned as a threshold. There are times where 1% is used. There are some times where 0.5% is used, or 10%. So there's no like set standard for it. But the most common one that I've seen used in my years of teaching stats is 5%. Okay, so in a Pew Research survey of 1,060 teens aged 13 to 17, it was found that 604, or 57% of those respondents, have made new friends online. This is something that happens with adults as well. I'm a testament to that. But I don't make friends with people in this age range. They're actually adults too. Okay, if the true rate is 50%, there is a probability of this, so point and then 5 zeros and then 306, of getting 604 or more respondents who have made new friends online. Is 604 significantly low, significantly high, or neither? What does the result suggest about the true rate of being 50%? All right, so what we want to do here is, first of all, compare this to the 5% rule. This is significantly smaller than 5%. So getting 604, what this probability states is that getting 604 simply by chance is not likely to happen whatsoever. So I would call this significantly high, and to verify that, we could do 604 divided by 1,060, okay, which is 57%. So this is higher, okay, so that's why we're going to use the language significantly higher or significantly more. And then what does this result suggest about the true rate of being 50%? If the true rate is 50%, then that assumption is wrong. So people are making friends more so online based on this information. So there's the solution to that. Okay, so the crown jewel of this section for me is a blind box simulation. So as I was sort of brainstorming ideas for this section, I recalled something that happened here at the Horshesky house a couple weeks ago, to give my daughter some driving practice before she turned 16. How do I say it? I convinced her to do some driving by rewarding her with some squishy dumpling rewards. So I'm saying this horribly. So my daughter wanted to get, or she wanted to go to Five Below to buy like these viral dumplings. And I said, okay, you know what? I'm probably going to have to buy these. So let's make a trade. I said, I'll buy you some dumplings if you drive us there. And so she flew downstairs, got everything ready, somehow magically found her driver's permit, glasses on and stuff, and she was ready to go. So I was like, this is great. And with these dumplings, they're blind boxes, meaning that you don't know which one you're going to get until you open it. And there's a certain rarity for some of these, and I forget one she wanted. I think she wanted one that had like some sparkly stuff in it. Um, and then there are the more common ones, which are just plain colors like pink, yellow, or blue. So I wanted to use that as my motivation for this section, and um, perhaps build something visual for my students with the help of Claude, of course. And so I went to Claude, and part of the reason for doing this too, um, yeah. So part of the reason for doing this too is so that they can get a better understanding of the three different approaches to finding probabilities. So I'll show you my original prompt. Okay, can you create a simulation that demonstrates the differences between the three common approaches to finding the probability of an event? In particular, the following approaches: relative frequency, approximation of probability, blah, blah, blah. And so it used a dice at first, which of course they're going to use dice all the time, or cards, or coins, or jars of marbles. And I was like, all right, well, here's a start. Um, so okay, I said, can you actually base it on a popular blind box series? And it was cautious, which is good. I want to make sure I do it right by you here, but I can't build this around a real blind box brand or as characters, for copyright purposes. And I said, that's fine. And here's what it came up with. It came up with these blind box toys. So Pip, Tuft, Glint, Mosley, Wobble, Squee, and Lucky Nimbus. And the simulation at first was, okay, open one box, and it creates a little diagram here where we can calculate a relative frequency, um, maybe work out the probability of getting it beforehand, and then a subjective probability. But what I did not understand at first was that the simulation was geared towards the Lucky Nimbus. And so I was having some trouble interpreting, okay, where are some of these values coming from? And then eventually it revealed that this is a simulation um, basically targeting the probability of getting the Lucky Nimbus. So while I'm thinking about all this, I wanted to see if maybe I could come up with some better pictures for these. And so I went back to ChatGPT, and let's see here. Character design request. I said, all right, can you create cool images of the following characters? And I just copy and pasted the description from Claude. And it came up with this picture, which I really like, but it was a little too dark for me. I wanted something a little more, poppy and whimsical, something for the girlies. And it came up with this, Pocket Pals. And I was like, this is perfect. I love it. Um, and so I showed my wife, and she was like, I think Ryan would actually like those, which is my daughter's name. Okay, so I decided to stick with this, and I'm going back and forth with Claude, and eventually we settled on, scroll down to it, this simulation, which is what I'm going to project on my screen in class. So this is just a simulation in Claude where we're going to look at the probabilities of, opening up a blind box and getting any one of those toys. And eventually it's going to unveil that the Lucky Nimbus is a real rarity. And so here's how it works. You can press the open one, and it just randomly picks one of those toys for you, and we get the mushroom, which is my wife's favorite. And you can see that this adjusted to show you the relative frequencies. So on our first pull, we got Mosley. As a relative frequency, that means there's 100% of getting Mosley, which we know is false. Okay, the theoretical probability of opening up any one of those cute little creatures here is 1 out of 7. Okay, so you can open another one. All right, and now the next one was Squee. So Mosley was picked 1 out of 2 times, so that's why its percent went down to 50. And now that this guy is in the mix, Squee has a 50% chance of being pulled as well, since it shows up once out of 2 pulls. Now, let me explain this right here. So it's asking, what is your subjective probability of pulling the Lucky Nimbus? And so what I want students to think about is this: why is it called Lucky? And if it's called Lucky, do you think the chances of picking it are going to be the same as the other ones, or would it be more or less? Hopefully they say less. Okay, so they get to adjust this down to whichever value they want. Maybe they say 5%, and it shows the 5% right here. Actually, let me go up to 7 so you're not confusing it with the threshold. Okay, so let's say it's 7% that they guess, and we're going to keep opening blind boxes and keep track of how many blind boxes were producing Lucky Nimbus. And so far, out of 7 boxes open, none of them have been Lucky Nimbus. Now, as you open more and more, the rest of the creatures make their way onto the scene, and you can see that the relative frequencies are adjusting. And in fact, they will approach a limiting value. And notice, even after almost 50 boxes opened, there have been 0 Lucky Nimbus characters. So you can skip by opening up 100 more or opening up 1,000 more, and you can continue doing that. And you see that these sort of stabilize here, and you kind of get an idea that the Lucky Nimbus is quite rare. And if you look at the percent that's being displayed, it's roughly 1%. And that's actually what the assigned rarity for the Lucky Nimbus is 1%. And so, this kind of gives an idea of the 3 different probabilities, okay? So this right here, this is the subjective probability, all right? So based on your experience with blind boxes or opening up anything that is a surprise, what is your suspicion that, or what do you think the odds are of you opening up something rare, okay? Then there's the theoretical, which is, all right, well, if everything has an equal chance of being selected, then pulling the Lucky Nimbus would be 1 out of 7. And then there's the relative approach, which we're seeing in this demonstration, okay? So based on historical data, 5,147 boxes being opened, well, it looks like the chances are actually more 1% or 1 out of 100. So this is something that I thought was kind of cool to demonstrate the differences between the 3 probabilities. And this is something that I'll be using in my class. If I tweak it and refine it some more, then that'll happen, and I'll be sure to update you guys on that. One last thing that I wanted to do, though, that I'll show you before I end the video, is I had Claude build some verbiage around the simulation. So I'm not just going to jump to the simulation and say, okay, guys, we're doing a simulation. I asked Claude to help me give the students some context. And so what I'm presenting here is something that Claude gave to me. I just copy and paste it, and I still have to tweak it a little bit. So this section of notes isn't completely finished. But I pretty much, thought that Claude nailed it with explaining what the simulation is meant for and some questions to sort of think about. And also, too, you'll notice that the designation of Lucky Nimbus being rare here isn't provided, and that's because I don't want to spoil it. So I had ChatGPT redo the picture without the designation of rare for Lucky Nimbus. All right, so it says here you're about to use an interactive simulation built around a blind box, which is a sealed box containing one of 7 possible mystery figures. One figure, Lucky Nimbus, is a secret rare. The other 6 are common. So it does actually expose that Nimbus is rare. However, it doesn't say how rare it is. So maybe I'll frame it that way. Okay, so the 3 approaches you're comparing sort of breaks it down with some formulas, and then how we'll actually run the simulation ourselves, and then questions to think about as you go. And there it is. All right, so thank you guys for watching another video with yours truly, Mr. C. If you have any questions, feel free to let me know. If you want any of the handouts or any of the prompts, let me know. I'll be happy to send those to you. In the meantime, let's keep bossing up StatCats, and let's get ready to knock out some more probability. It might not be my favorite, but I'm having some fun with it, and hopefully you are too. All right, have a great one. Let's boss up.